which focuses on machine learning and artificial intelligence with particular emphasis on causal discovery and inference, causal representation learning, and machine learning under data heterogeneity. So his work aims to enhance the transparency and interpretability of causal learning and reasoning in science. So he's also an associate professor at Carnegie Mellon University in the state, where he explored advanced topics in machine learning and AI, particularly causal learning and reasoning. His contribution have significantly shaped the field, deriving innovation in both theoretical and applied aspects of artificial intelligence. So we are happy to have you here, and over to you, sir.
Thank you so much. You can hear me fine, right? Thank you very much for organizing this great event, and thanks for the invitation. So this afternoon, I'm going to introduce causality, an emerging research topic in AI and machine learning. So in the first class, I'm going to give an introduction to causality. Let's see what do you mean by causality, how to define causality, why is causality so useful? And then let's see how we can do a classical problem, which is a causal inference or identification of causal effects. And then let's see how we can do
recording in progress.
Reasoning. And after that, in the second lecture, I'm going to talk about how to discover causality from data. Okay. And tomorrow, we are going to go further. We see how to discover latent variables from data and how to use causality to benefit generative AI. Okay, so right here, this is the outline. It's a lot of things. I hope we can finish everything very quickly. But if you have any questions, please just let me know. Okay. So let's start with some examples. Right here, you can see in the Telegraph, you can see this news report. They say couples who share housework are more likely to divorce. Okay. So first of all, they did some statistical analysis. They collected data. They found that actually divorce and sharing housework are correlated. But for us, this is meaningless, right? We have to figure out what we can do in order to improve the situation, right? So statistical information is not meaningful if you try to make the desired difference. And that's why it's not a surprise that there was a lot of follow-up discussions right here. As you can see from here, that sharing housework really leads to divorce. Let's try to figure out the causal relation, because we always try to understand things so that we can do things better, right? Association information is not useful for that purpose. So right here, this is the second example. Right here, x-axis is the chocolate consumption per capita per year, and the y-axis is the number of Nobel laureates for 10 million people in the country. So right here, you can see if you take log transformation, the correlation is very nice. The relationship is almost linear, right? So why? Basically, do you think we should just distribute the chocolate to everyone every day so that we can have more Nobel Prize winners here, right? So clearly, we try to see the underlying causal relations. Later today, you are going to see that actually, just from data, we can discover that they are the hidden variable as a common cause for chocolate consumption and the Nobel Prize winners. There are no direct causal influence in between, so we don't have to distribute the chocolate every day. Now you can see, once again, correlation is useful for prediction, but if you really want to see how to make things better, we have to go to the level of causality. Now let's look at something that does not seem relevant. So, everyone talk about generative AI. So let's see how generative AI, specifically image generator, works. So right here, the prompt is a peacock eating ice cream. It's good, right? For you, although we are not really kind of artists, right? We can still draw some picture with the peacock ice cream, and we know how to put them together, right? And here, more than 1 year ago, this was the result produced by Stable Diffusion. There are no ice cream. Of course, it's random, but basically it's because in the training data, there are no kind of similar image, right? You have to go beyond the data or go beyond the training data. And this is problem known as extrapolation. We can do it because we understand the concepts and the relations among the concepts. But here, for machine learning systems, it's very hard to achieve so. 3 months ago, with the DAO 3 by OpenAI, now it's much better. However, if you have a closer look, you can see very oftentimes Peacock is using human hands right here. And it's not really eating, you can see it's touching. So you can see a lot of problems, right? Once again, they can produce very fancy images. The problem is they cannot really go to the level of concepts and the relations between the concepts. For us, right? The picture may not really have very high quality, but we can produce a very sensible picture. And now with our platform, you can see, yes, people can eat ice cream, and later, tomorrow, you see, we can even just change a particular thing, say the color of ice cream, while we can keep everything else the same. So this way, you have to make sure machine can really understand what you say. Machine understand what you mean by ice cream and what you mean by white. And then you can just change only the color right here. Okay. So now this is another illustration. So with DAO3, again by OpenAI, now you can see we can produce very nice pictures, right? This is a female face, and right here is a smiling girl in garden. And right here, if you ask the OpenAI, the platform DAO3, to add mustache, you can see basically nothing happens, right? We can do so. We know where to put the mustache, right? We know how to do it. Although this is a little bit weird, right? But we can do it. And but for OpenAI, it's almost impossible. Okay, and similarly here, if you try to do the editing to just make the girl say surprised, then with this platform you can see everything becomes different, right? And with our platform based on causality, now you can see yes, you can generate an image, female face, and then you can just add mustache, and you can generate a smiling girl, picture of smiling girl in garden, and then you can just change the facial expression right here. So basically, with the causality or with some causal principles, we can really go to the levels of concepts and make necessary changes in a very controllable way. Okay, now what's causality? So how can we define causality? Any idea? How can we define causality? First of all, we cannot define causality just in terms of statistical information like a correlation or dependence, right? So we have to go to another level, because the causality is about the changes and the consequences of changes. Sorry? Yes, so basically, how can we define cause-effect relationships? Right? We use it every day. Yes, so what do you mean by cause it? Right now you can see it's circular. Actually, even the fundamental definition, this definition is still circular. You're totally right. However, circular definition may be very useful. Later you can see how we can break the circle and discover causality from data. So we know we say two variables or two events are associated only if they are not independent. It's very simple. And we say X is the cause of Y if this is true. And we have to define do. Now you can see in addition to the traditional notations, we have to define new one, intervention, do. So at CMU, Peter Spertis actually proposed a set. He used a set. And Prof from UCLA used do. But the do became more popular. Okay, let's use do. But basically the same. In some papers, you can see set. It's the same thing. Right here. So do is the intervention. Basically, when you do intervention on something, you only directly change this thing without directly changing any other thing in the system. So now you do intervention on X to set the value of X to different values right here. And then if you can see the difference in Y, distribution of Y, then we say X causes Y. Why? Because the definition of intervention, we know we do intervention on X, we directly change only X, but not anything else in the system, right? And now you guarantee that's the case, and then you observe the change in the distribution Y. What does it mean? That means, yes, this change in Y must be caused by the change in the X value because of intervention. That means there's a way for X to influence Y, right? So of course, this definition is still circular. Why? Because suppose I have no idea about the causality, how can I make sure this is intervention without changing any other variable in the system? I cannot guarantee that, right? So that's why the definition is still circular. But later you can see by introducing some assumptions and kind of data analysis method, we can break the circle. We can even discover causality from data, from purely observational data. Okay, this is the causality. So we know what we mean by intervention. We know we have to define causality intervention because this is a kind of controlled change. I only make a difference here, and then if I see a change in some other variables, I know there must be a pathway for this guy to change that, right? So we can define causality. Then this is the classic way to discover causality. We try to do interventions. Or later, see, we can also try to do controlled and randomized controlled experiments. So they are similar here. By doing interventions, by imagining doing interventions, you can verify that the rain is the cause of wet grass and hot weather is the cause of ice cream, and so on, high sales of ice cream and so on. Let's look at this example. Suppose I go to work by bus around 8:30. I'm leaving home. At the same time, the bus is coming. So there's a very high correlation, right? Is there a causal inference in between? Do you think one of them is the cause of the other? Now let's do intervention. Yes? Yeah, you know, right? That's something on your mind. It's different from really kind of. Yeah. Then you are saying the intention is the cause, but the intention is different from bus coming, right? So here, let's do intervention. So suppose the bus is coming right here. I just jump in front of the bus, right? Hopefully the bus will stop. This is intervention because I directly change bus without directly changing this guy. Now you can see this guy will still leave home as usual, right? Because the guy cannot see it. So clearly this is not a cause. Similarly, when the guy is about to leave home, I just lock the door. The guy will stay, the bus will still come, right? So you can see there are no causal influence in between. But still clearly they are dependent. Why? Because generally speaking, we have a timetable as a cause. So we follow timetable. Both of them actually follow timetable. And that's why you can see the coincidence, right? By making use of intervention, you can really verify a lot of causal relations. But we know it's very hard to apply interventions because you have to make sure this action changed only this particular variable for now. Okay, so this is how we can represent the causal relations. Right here, we use direct links. If there's a direct link right here, it means that drinking is the direct cause of smoking, right? Similarly, drinking is the direct cause of cancer and so on. So the causal graph is very simple, right? When we were very young, we use a direct representation, as you can see from here. And furthermore, you can see here, there are two pathways, direct influence and indirect causal influence. If you have a graph, you know not only causality, but also direct influence and indirect causal influences. That's very nice because this way I have freedom. I know what to change in order to achieve my desired difference while I can still keep something the same. Later, I'll give you an example. This is how we can represent the causal relation with the graph. Okay, so basically in machine learning, in AI, there are three typical questions. The first one is the prediction. You have data, as you can see from here, and then you try to say, would the person cough if we find or we see he or she has yellow fingers, right? This is purely observational. We have data, we try to make use of some kind of conditional distribution to make prediction. That's it, right? You can do regression, you can do deep learning. So statistical information would be sufficient in this case. In the second one, we would like to see the effect of interventions, right? We try to see, say, whether vaccination is effective. In other words, we try to identify the effect of vaccination, right? So similarly, here, the question is as follows. Would the person cough if we make sure he or she has yellow fingers? When you say we make sure something happens, you just do it, right? Or here, I apply yellow fingers, and right there, I don't apply yellow fingers, right? You do intervention, and then try to see whether is the intervention has a consequence. So a classical problem is to consider treatment effect. Here, I have two groups of patients. Right here, I apply treatment, and here, I don't apply any treatment, right? They're in a control group. I try to see whether the treatment is effective. In other words, we try to identify the probability of the target variable or effect given the intervention on what we can change, like treatment, right? This is known as treatment effect or causal effect. Later, you can see how we can identify this causal effect from data and the causal graph. And this is a classical problem. This problem is known as causal inference or identification of causal effects. The third one is known as the counterfactual question. This is actually the ideal way to achieve personalization. When we say, oh, I really understand you, or you are so unique, what does that mean? It means that you can discover the hidden features of this person that others cannot discover, right? You discover hidden features like a noise term. Nothing is a noise. We say the noise just because we cannot directly measure it, right? So from the causal perspective, later you can see how we can discover the noise term of the person and make use of it. This is a counterfactual reasoning. So typical question is as follows. We are considering a particular person or particular set of persons. Would George cough had he had yellow fingers? Intervention. Given that he does not have yellow fingers and coughs, so we observe something about George. This person, George, does not have yellow fingers and he coughs, right? And given that, we are trying to see what would have happened to the same person if something had been different. So what if, right, would George cough had he had yellow fingers? We do intervention here and we try to see whether the person coughs, right? So this is called counterfactual because clearly this is what you observe, this is the fact, right? And now you try to see how to make a difference, right? Clearly it's imaginary and it's that's why it's called counterfactual, but it's very useful. Whenever we try to see whether anyone in history was a good person, we try to answer this question, right? What would have happened to history if that guy had done something different, right? So by doing this kind of comparison, we can try to see whether that guy, right, in history really was a great guy, right? Making a lot of contributions to the historical development and so on. So this is the way for us to really see, to do reflection, self-reflection. And then by doing this, you can try to see in this situation, how to make the situation better. Okay, later you can see how we can answer such questions. Now let me give another a few examples to illustrate why we care about the causality. First of all, we distinguish between dependence and causality. This example used by Fisher, Sir Fisher, the statistician. So basically, if you try to change the incidence of lung disease, right, change the yellow finger would not be helpful. But although they are dependent, you have to go to the causes to make a difference, right? So this is very clear. And now comes the second example to illustrate Simpson paradox. So this is a real data set published in the 1970s. So here in the hospital, there are two treatments to treat kidney stones. We have two groups of patients with small stones and large stones. Okay, we are considering kidney stones. So now you can see for the group of patients with small stones, A is better, right? And for the those with large stones, A is also better. As you can see from the higher recovery rate, it's higher. 93% versus 87%, 73% versus 69%. So A is better, always better, right? Across the two groups of patients. However, if you put the data together, just put data together, and A becomes worse, B is better, as you can see from here. Now, suppose you are a doctor, and suppose you only care about the recovery rate. You just try to maximize the recovery, the chance of a recovery. So, and now comes a new patient. You have no idea about this patient. Okay? You don't know whether stone is large or small. In this case, would you recommend A or B? B? Okay. B? Will you recommend B or A? B or A? B? 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 A? A? Okay, now it's nice, right? You can see conflict, and then we can have new ideas. So A, B. Now you can see why it's called a paradox. If you know the stone is small, would you recommend A or B? A. If you know the stone is large, would you recommend A or B? A, right? A. Okay, now. A is better. Yeah, it doesn't matter. This is the recovery rate, right? We just care about the chance. Is that right? So the chance is higher. This is the recovery rate. So now that's why it's called a paradox, right? Of course, the paradox is not really a paradox. It's just a trick. So now you are saying, if it's small, I recommend A. And if it's large, I recommend A. Now the stone is either small or large. Therefore, my answer would be A or A, which is B. Right? So basically here, later you can see why we cannot trust this rule. We cannot trust this the data right here. We would like to recommend A or A, which is A. Later you can see how we can answer this question. Why? The problem is that follows. This rule let's talk about the association of information, the dependence between treatment and recovery. However, in this case, the stone size is a common cause of treatment and recovery. And for that reason, although we care about only this influence, when we make a recommendation, we only care about this influence, the influence from treatment to recovery. We don't care about stone size because it's given, right? So this property can be totally different from the dependence pattern between treatment and recovery. Okay, that's why. So here we have to infer the causal effect represented by this question mark right here. Okay, and this causal effect right here can be totally different from dependence given right here in the last row. Okay, later you can see how we can, yes. If you just care about ratio right here, right? You don't just care about ratio. Is that right? Then you should clear here. Oh, this is the chance is clear higher, right? Higher, and therefore I would recommend A or A. Is that right? So finally, the answer is A. And later you can see actually the answer would be A. We can just answer this question in a principled way by doing identification of the causal effects. Yeah, but this is nice. Now you can see B. Clearly, this is also in some way this is sensible because if you put the data together, B seems to be better, as you can see from this example. Okay. So this is similar. X is the exercise, Y the collateral. So we know now you can see we have different age groups. Those are in the 50s, those are in the 40s, and so on. We have different people, right? Right here. Now you can see in each age group, the more exercise you do, on average, the less cholesterol you are going to have. That's good. That means we should try to do more exercise to reduce cholesterol, right? Good. Remember this pattern. So now clearly you want to recommend anyone, right? Just do more exercise. But if you put them together, forget about the age information. Similarly, previously, if you forget about the stone size information, you only see this dependence pattern. Now, you can see they are positively correlated, right? And this is also true. If you just want to make prediction, this is very useful to say, oh, on average, the more exercise I see, the more cholesterol. Yes, right? This is the correlation, high correlation. But this is, now you can see we use C for prediction. Here we use do. We try to see how to reduce cholesterol. Okay, so now you can see, yes, negative effect can become positive correlation if you ignore that guy, because the correlation can be totally different from causal effect. Once again, it's the same pattern because we only care about this link right here. Okay. Now comes another example. Later you can see how we can answer this question. So in the United States, so if you go back 60 years, you will see that on average, female college students were smarter than male students. Why? We believe that in the population, the females and males are kind of equally smart, right? So, but at that time, female college students were clearly smarter than male students. And this is known as selection bias. So at that time, it's pretty hard for the females to be admitted to college. So gender and IQ are both causes of being admitted. And then now you can see, although originally, considering the whole population, gender and IQ were independent, given that you are considering only college students, the consequence, they will become dependent. You can think of X, Y, X plus Y, right? If you know X plus Y, then X and Y will be perfectly negatively correlated because the sum is given, right? That's conditional. So now you can see why female students were smarter than male students because it's harder for them to get admitted, right? So this is called selection bias. Selection bias is almost everywhere. If you pay attention to the polling results for the presidential election in the States, you can see every time there was a selection bias. Now comes another example, which is similar. This is a basic illustration of the survivorship bias, right? So in World War II, you can see a lot of aircrafts came back and they can see the damage right here. Now they try to see where to put armor in order to increase the chance for the aircraft to come back. Would you like to put armor here in those areas that are not damaged, or right here? All right. With damaged part A, the areas that are not damaged, B, A or B. Damaged, not damaged. B, wonderful. Actually, at the very beginning, the military gave an answer. They said, oh, we should put the armor here. And then the statistician, Ward, Ward test, the Ward guy, Ward basically provide the answer, said we should put armor right here in the areas that are not damaged. Why? Because if you have, now we have a story, being hit, where are causes of survival. And you only observe the aircraft that successfully came back, right? Corresponding to survival equal to 1. And we try to infer what have happened to the aircraft that failed to come back. Then, basically they got hit in those areas. Then we know we have to make a difference, right? Okay, good. So now let's have a look at the graphical model. I just try to explain one concept in graphical models, which is deseparation. Why? Because if you try to use a graphical criteria to do causal effect identification, then you have to use a blocked path or deseparation. I'll explain what I mean by deseparation. So we use the graph to represent the causal relation. As you can see from here, each link is directed, and here you can see the terms. Graphical models are very simple because they are very intuitive. So each of them is a node, this is the edge or link, and if there is an edge in between, we say they are adjacent. And if you ignore the directional information and just follow a set of consecutive links, then we say they are the path. So here, they are the path from x1 to x3 this way, then another path from x1 to x3 via x2. So if you just go this way, it's a path. Okay, it's just a set of consecutive edges. And then here, x1 is the parent of x2 because x1 directly gives rise to x2, right, parent. And similarly, x4 has two parents, x2 and x3 right here. And x4 is a child of x2 and x3. And since they have a child, x2 and x4, x3 and x2 are spouses. Okay, if they have a common child, they are spouses. They are spouses. And we define ancestors and descendants recursively. First of all, a parent is an ancestor. And then the parent of an ancestor is also an ancestor. Basically, you can just go to earlier parents, right? All of them are just ancestors. And similarly, descendant, a child is a descendant, and a child of any descendant is still a descendant. So you can just define ancestors and descendants recursively. And Markov blanket is also useful, but here it's not very relevant. I'll skip this one. Okay, so here you can see an example. This is the directed graphical model, also known as a Bayesian network. As you can see from here, there are two components. So one is a graphical specification, graphical model representation. So graph structure, this is qualitative information. I have a structure. And the other is to specify the conditional distribution information. Here, I consider discrete variables, so I just have the conditional distribution table, right? And in the linear case, you can have a regression model to specify the conditional distribution of one variable given the parents, right? So if you have two, then it's a graphical model. You have a graphical representation together with a probabilistic model to specify the conditional distribution. That's it. Okay. Now, we are given two graphs. Consider each of them. What independent relationship can you see? Can you see any independence or conditional independent relationship? By the way, do you know conditional independence? Independent. We know independent. X, Y are independent if the joint probability distribution is the same as the product of the marginal one, right? In other words, if the conditional distribution Y given X is the same as the marginal Y, then they are independent because knowing X does not contain any information about the Y. They are independent. And when we say X, Y are conditionally independent given Z, we mean for any fixed value of Z, X, Y are independent. Okay. So now, can you see any conditional independent relationship from this graphical representation? For instance, do you think given smoking, do you think cancer and yellow finger will be independent? Yes. Yes or no? Yeah. Yeah. Can you say a few words? Why? No. If you fix the value of smoking, yes, yes. So now, suppose this is the truth. Let's just follow this representation. If this is the case, meaning that if you fix smoking, right? If you fix this value, then they are not related at all, right? If you fix this one, then this is the only way for them to be related, right? So they are conditionally independent because for fixed value of smoking, they are independent. Cool. So now, similarly, right here, can you see conditional independent relationship? So this is the basic grandpa or grandma, this is a parent, and this is the child, right? Now you can see here, this is fine. However, if I fix the value of parent, or consider particular value, right? Fixed value, then this would not be relevant because all the influence takes place via this guy. If I fix this one, then they are independent, right? So similarly here, given slippery ground, rain and falling down will be conditionally independent. Okay, and this is known as local Markov condition. It says each variable is conditionally independent from its non-descendants given its parents. So each variable is conditionally independent from its non-descendant because this guy is not descendant given its parents. Similarly, this guy is conditionally independent from its non-descendant, which is not the descendant given the parents. So this is called local Markov condition. Okay, it's nice. Basically, given parents, I'll be independent from my ancestors, right? And that's it. Now let's go further. Suppose you are given an arbitrary directed graph, as you can see from here, and you try to see whether any two arbitrary sets of variables are conditionally independent given some other variables. What can we do? We do not always condition on all the parents, right? So here we have to introduce a concept of deseparation proposed by Yuda Pearl. So right here, we use a deseparation. And if every path from node X to node Y is deseparated by Z, then X, Y are always conditionally independent. D stands for this direction. Okay? Because when we try to determine whether they are deseparated, we care about the direction of the edges. Now let's see the definition. Okay, this is probably the only technical slide. So, but this definition is very, very important. Why? Because with this definition, we can easily see whether any arbitrary variables in the graphical representation are conditionally independent given any arbitrary variables. Okay. So we say a set of nodes Z, any variables, D separates two sets of nodes X, Y. If every path from a node in X to a node in Y is blocked given Z. Okay, now we have to see how to define blocked path, right? Path blocked. So we say a path is blocked by a set of nodes Z if at least one of the two conditions holds true. Okay, or relationship like that. Right? We use all here. The first condition says this path contains a chain or common cause pattern while the middle guy is in Z. Okay, so because here, if you fix M, there are no information flow. Here, if you fix M, again, there are no information flow. Okay, or T contains a path, contains a collider or common effect M, while this guy M is not in Z and no descendant of M is in Z. I do not condition on the effect. Then they are the path is blocked. Now let's look at some examples. Given this graphical representation, do you think X and Y are deseparated by R and V? Yes or no? Do you think X and Y are deseparated by R and V? Yes or no? To save time, yes, because here you can middle node. This middle node is there. The first condition holds true, right? Do you think S and U are deseparated by R and V? is U, let's just use the definition. Is U D separated by R and D, yes or no? Is the first condition true? First one is not true, right? The second one holds true. Or, therefore, this part is blocked, right? And this is the only part. That's why S and U are D separated by R and B. Okay, we just apply the criterion. Why? Because given RU, I don't care. This is the common effect. It's not given. They can change in free way. So there are no association in between. So they are D-separated. Here, let's look at only one example. Do you think X and Y are D-separated by RP? RP. Let's just apply, wow, time flies. So let's apply the criteria. X, Y, D-separated by RP, yes or no? Middle node, the first condition holds true, right? Because this guy, R is here, middle node, R is given, therefore, the blocked, right? Okay, so just apply this. Good, I'll skip this part, you can see more examples. But basically, why do we care about that? It's because we have a global markup condition. Given a DAG, let X, Y be two variables and Z be a set of variables. And then if Z D-separate X, Y, then they are condition independent. Okay? So now see, yes, as long as they are D-separated, they are condition independent, no matter where they are. And if you have a DAG, then the two conditions, local markup condition and global markup condition, are equivalent. If you have cycles, they are not. They are not equivalent. Okay, so now let's go to next part. Let's have a very quick look at identification of causal effects. The second one, right? We try to answer the second question. So what do we mean by causal effect? Basically, a fundamental way to define causal effect is to write down the probability of the target variable, say, recovery, given the intervention on the variable you want to change, the treatment. So this quantity is known as causal effect. And specifically, very often it's also called treatment effect, because it's the effect of treatment on recovery. Okay, it's just a probability involving interventions. The classical way to find the causal effect is to do randomized controlled experiments. I have a lot of patients here. I divide the patients into two groups, right? The control group and treatment group. I have to make sure that all the remaining features either have the same value or have the same distribution. That's it. I have to make sure all the remaining features either have the same value or the same distribution across the two groups. Then this value is different, right? This value is different. If I see a difference in recovery, I know our treatment must have an effect on recovery, because that's the only variation, right? And this is the way to identify causal effect. But we know it's very hard. First of all, we don't have access to many features. A lot of features are not measured, right? And second of all, even if you can do this, very often times you don't really have very clear quantitative information. You can just say, oh, here, there's the effect, but you don't have a model, quantitative model. Okay, now let's do causal effect identification or observational studies of causal effects according to Daniel Rubin. So we make use of the observational data instead of randomized controlled experiments. At the same time, make use of graphical representation. So with the two sources of input, we can identify causal effect. One is the graph, called graph, the other is the observational data. Okay, now let's see the basic idea. Let's come back to this example. We try to see the treatment effect, the effect of treatment on recovery. We try to answer this question, right? Both equations hold true. The first one is the conditional distribution of recovery given treatment. Clear, this is true. And this one explains the last row. If you just use this one, then you have the conditional distribution, conditional information. That's true. However, now we do intervention. If you do intervention, what do? You just directly change the value. If I do intervention here, I directly set the treatment to either A or B. Then the original mechanism will disappear. I cut off the links, right? Because they disappear. I directly change the value. And as a consequence, after I do intervention, they will become independent. And then now you can see this is the only difference. The conditional distribution of stone size given treatment will become the marginal distribution of stone size. That's the only difference. Because I'm doing intervention. If I do intervention, then the original mechanism will disappear. As a consequence, the conditional distribution will become marginal. Because now they become independent. If you use this equation, now you can see, yes, we can identify cause effect. So here, you can see for small stones, for the patient with small stones, B is worse, A is better. But here we have more people, as you can see from here. We have more people here. And for those with large stones, A has more people, as you can see from here, right? And if you consider average, it's always a weighted average. If you consider average, since I have a lot of people here and a lot of here, you can see this average, B would be better. Okay, corresponding to the last row, B would be better. This is because I always use the conditional distribution as a weight. Now, if I use the marginal one, now you can see, yes, I just use the marginal one to consider the weighted sum, and then A would be better, as you can see from here, right? I just replace probability distribution of stone size given treatment with the probability distribution of stone size. Okay, now you can just get the correct answer. So here you can see we just follow the definition of intervention and then can identify treatment effect this way. Okay, this is the basic idea. Now you can see it's not mysterious. We can always do so. Why? Because you just try to imagine how intervention can be applied, and then you just try to follow a new graph where you have intervention, and as a consequence, you cut off some links. That's it. Okay. Now let's look at more details. So the first problem here is the identifiability of causal effect. And you can see a lot of classical causality people, researchers, including Prof, Daniel Rubin, Prof from UCLA, Daniel Rubin from Harvard, made a lot of contribution just to this problem. They try to see the conditions on which the causal effect is identifiable. In order to define identifiability of causal effect, let's try to remember the identifiability of parameters in a statistical model. So it's very simple. But in any textbook, you can find it. So you have a parameters, and you have models specified by the parameter. So if different parameter values correspond to different distributions, or equivalently, as a counterpositive, the same probability distribution always gives rise to the same parameter value, then we say parameter here is identifiable because two parameter values will correspond to different observation distributions. Okay, this is the identifiability of causal effects. Identifiability of parameters. Similarly, we have identifiability of causal effects. Okay, so this is the causal effect. Now we make use of two things to solve the problem. Sorry, mean of Gaussian distribution, it is identifiable because different means, different values of mean will correspond to different distribution. Right? That's why it's identifiable. Okay, so this is the causal effect, and then we just try to the definition as follows. Suppose you have two models with the same causal structure, given structure, and the same distribution for the observational data or observed data. Suppose this is the hidden. Then you only have this structure and the data for those two observed variables right here. Now, if they always give the same causal effect, then we say the causal effect is identified. It's the same thing. I try to see whether two different models can give rise to. I try to see if the structure and the distribution of the observed variables are the same, whether the causal effect is the same, right? If that's the case, we say it's identifiable. It's the same thing. Okay. Why do we care about it? Because if it's not identifiable, then it makes no sense to talk about the causal effect. Because given the structure and the observed data, you cannot determine it. You want to find the truth. There's a big difference between causality research and traditional artificial intelligence or machine learning research. In causality, we care about the truth. right? You try to recover the truth. That's why you have to care about the identifiability. But in machine learning or in prediction, we care about optimality. As long as you can make it better, I say it's good, right? But now, if it does not convert to the truth, it may not make sense. Okay, so this is the definition. And then now let me give one model in which the causal effect is not identifiable. Suppose here, you can see right here, this is a graphical representation, age, xi is cholesterol. Suppose age is not given. We don't observe age information. We only observe xi cholesterol information distribution given here. Okay? Now you can see it's not identifiable. Why? Because with the same distribution and same structure, the parameters can be very different. Right? They can give the same distribution of the observed variables. As a consequence, they correspond to very different parameters. It makes no sense to identify the effect of xi on cholesterol. Right? So it's not identifiable if age is not observable.
Check the identifiable parameters from this.
Sorry, can we?
Number if you have data.
Yeah.
Then we say identifiable parameters from this.
Can we
Extract. Can we extract the identifiable data?
Oh, you mean suppose you are given a graph, right, and the data you want to see, determine, you want to figure out whether it's identifiable.
Yeah.
Yes, that's a good question. Later you can say yes, we have some criteria, and actually that's a contribution made by Daniel Rubin and Prof and also Peter Sabatis. They care about the conditions under which the causal effect is identified. Exactly, that's a big problem.
Not the size of the stone. Then option B would have been better, but if we knew the size of the stone, then we would have decided which will take.
You're totally right. Because in that case, it's not identifiable. Makes no sense, right? But if you know it's not identifiable, I have to collect more evidence in order to answer the question, right? Okay, wonderful. So now comes the potential outcome framework proposed by Daniel Rubin from Harvard. In statistics, a lot of people use the potential outcome framework. Let's make it very quick. I will explain why it's called a potential outcome. So here, we try to infer the effect of a treatment or kind of policy, right, on some outcome. So we have Y as a target variable or the outcome, and we have T treatment or the variable you can do intervention on right here. So if you observe those guys, the effect of intervention, then everything is given, right? It's very simple. And here, let's see the definition. T is the observed treatment, Y observed outcome, I is a specific unit of subject. And then this one, YI1, means the potential outcome if the patient I had been treated. It's just a notation. I's notation, I's patient treated. Right here, the I's patient not treated. Okay? So this is just outcome. First of all, it's an outcome. Second of all, it's a potential because at the same time, at most one of them is observable. For me, if you do intervention or if you do treatment, then you cannot observe the outcome without treatment. Right? Even if you can do it later, I will become different. Right? That's why you can only observe at most one of them. That's why this is called a potential outcome, because you cannot observe them, although they really exist. Okay, so this, and then if you have access to those two guys, then causal effect is very simple. You can see the difference, you can see whatever you like, right? Because everything is transparent. Okay, so that's why basically causal inference is a missing value problem. I have missing value here for this. For the first subject, I didn't apply intervention. I observe this value, but I cannot observe this value. So there are always missing values. But I want to identify this because I try to see whether treatment is effective, right? I want to see the difference. So you have to estimate the missing values. Without proper conditions, we know it's not possible, right? Okay, now let's see. This is why it's called a potential outcome. And here you can see the setup of potential outcome framework. We have a set of ID subjects. In subjects, we observe a top for each of them, consisting of the feature or covariate vector, X, like age, body height, body weight, and so on. And we have treatment, assignment, 0 or 1 in the classical setting, and we have response outcome y. We observe those things, okay? And then we know there are potential outcomes, and we try to infer the difference, right? That's the causal effect. Okay? So our first goal here is to estimate the average treatment effect. By average, I mean you just consider expectation across all subjects. That's it, right? How can we answer this question? Basically, in order to answer this one, we have to make some assumptions, as you can see from here. This right here, there are 5 typical assumptions you have to make in order to identify causal effects. Maybe we should take a break, and then we can continue.
Okay, thank you so much for your nice talk. So there are a bundle of questions that are arising. My first question would be, and then from the audience, maybe 2 or 3 questions. In high dimensional data, you may say in big data, to find the true causes is not a computationally expensive. It's a a big challenge for the to find the true causes in high dimensional data.
Wonderful question. 30 years ago, it was not possible to find the true causes. And 25 years ago, it was really, really challenging. But now, because of the new methods, I can give one example. If you use a method called FGS, fast GS, fast greedy equivalent search method, then you can find a causal graph over 1 million variables with 1,000 data points within 1 day on your laptop. So right now, there are a lot of efficient methods to discover causal relations, especially in the linear case.
Okay. So, thank you so much. But one is, if you find the true causes, it can help us, how much it can help to cover the problem of hallucination in LLMs?
Oh, that's a very good one. Actually, we have some ongoing projects on that. So I would say it's still complicated. I would say it's still complicated. So basically, LLMs make use of dependence patterns, right? The dependent patterns. And if you can decompose the dependent pattern to different kinds of properties, right? You have a causal relation and logical relation and so on. Then hopefully you can reduce the hallucination phenomenon. And roughly speaking, so we have some ongoing work on that. But still, if you don't have data at all, then in that case, you only have 2 choices. One, to allow LLMs to say, I don't know, right? The other is basically generate something rather random. So I would say, yes, that problem can be solved. The causal principle can provide some hints, but still there's a long way to go.
Okay, anyone? Any question?
Yeah, is this possible to actually know what is the true cause? So you are saying that it's a true cause, but how do I know? It's a more philosophical question that in the world can be established what knows.
Wonderful. That's the next lecture. It's known as causal discovery. That's a classical problem. Under some assumptions, which are usually testable, then you can really see whether it's really true cause. You can do that. I will give a lot of examples. In about 40 minutes, you'll see examples.
Thank you so much. Thank you so much, sir.
Thank you. Let's. How long the break?
It's up to you.
Okay, up to you.
It's okay for you?
Oh yes, for me fine.
Okay. So about the next lecture, it's the causal discoveries and